I am Peter Solagna. I'm working for EGI.eu and I'm operation manager. I'm currently leading the operational activities within the EGI. For EGI, this is a webinar about the EGI solution for high-throughput data analysis. What does it mean, high-throughput data analysis? Let's say that high-throughput computing can be described as a use case for an infrastructure that includes big numbers of tasks that could be data analysis tasks, so computing jobs for analyzing data, or other similar tasks that are submitted in big numbers and that are loosely coupled. Tasks that can be executed individually, so they don't need to interact much. And so what users do usually is to submit these tasks to the infrastructure, big numbers of them, and then collect, once they have been scheduled and executed in the distributed resources of the infrastructure, they can collect the outputs from the services that have executed their jobs. So this is an outline of this presentation. I will start with an overview of the EGI infrastructure, the EGI structure. Then I will go through describing the targets, the purpose of the high-throughput data analysis solution. That is the main topic for this webinar. And then I will go through the different layers, the different type of services that we are providing to our users. So how users can access the infrastructure, how they are authenticated, how they are authorized to access services, services for data and storage, and services for computing activities. The European grid infrastructure covers over 35 countries in Europe, and it is currently sustained by driven by a European funded project, EGI Inspire. You can see here in the map the partners of this project. Grid means that the grid aims to share and federate in a secure way distributed IT resources, part of this infrastructure. These resources can be either compute resources, so execution environment for computing tasks in clusters distributed in many resource centers over Europe and also outside Europe. Data infrastructures, that means storage servers where users can upload and store their data, their files in a distributed manner in the different resource centers, but also to put together this distributed, let's say, amount of resources. There is need also for other activities. So EGI provides also federated operations that are constituted of global tasks. That means central activities, central services that are needed to federate the different resources, different resource centers, and also global, also let's say distributed operation activities that are carried out by the different countries, the different national grid initiative that are basically roughly one per country of these 35 countries in this map. Also NGI, so the National Grid Initiative, are also carrying out user support, and also EGI centrally is providing user support and coordination for these activities. And also there are other other tasks, other activities that are part of the, let's say, European grid infrastructure activities. So as I was describing in the previous slide, the, the resource provider, the key providers for EGI are the national grid infrastructure, which put together, let's say, federate at the national level the resource center participating to EGI, and then act as a single point of contact for these national resource center at European level. So usually EGI centrally liaise with the NGIs, who are then liaising with their national resource centers. We have around 330 resource centers, so sites providing resources distributed in Europe, mainly in Europe, but also in Asia and South America and in Canada. Currently, the infrastructure provides around 400,000 cores and 190 petabyte for storage capacity. So what are the targets of the high throughput data analysis infrastructure? The target customer for these solutions, for this set of services that I will be describing today, are the research communities who need to store, analyze, and produce large data set of data. What are the issues that these services that we are providing address? Often user community have access to resources, let's say distributed resources. Let's think about cooperation, collaboration, research collaborations that are involving different research center, different universities, for example, and all of them have their local resources. Now, these local resources currently usually are can be easily accessed only by local users, because they have their authentication, they have their policies, they know the IT department, they can go to the IT department asking them to enable their user on that cluster. But when researchers need to share their activities and their resources, so now at that point in time there is need for a more homogeneous and coordinated operation of the resources. So they are not uniformly accessible. And also all these services that I will be describing allow, beside let's say the basic access to resources, also there are tools to allow users to manage big amount of data in a collaboration. That means that authorization and access control can be let's say regulated by the research collaboration in a central manner, and uniformly deployed in the distributed part of the infrastructure. And also there are tools to, let's say, to manage and to handle big amount of data, to transfer them, to have catalogs of these data in order to make it easier, because of course as the data increases, and also as the users are managing, let's say, the data storing data in a distributed way, this requires additional tool to make sure that all this distributed data comes together when there is time to use it and to access it. What we are providing is easy access to shared computing and data services provided by independent resource provider, and in a uniform way, optimizing usage. Uniform way means that we are based on open standards, open source middleware service. So most of the software we are deploying in the resource center is open source, and it is based on open standards. We allow data access based on the virtual organizations, which I will describe just a few slides later, and they are basically the user structure that we use for access control and to grant access to the resources. And also this, in order to optimize the usage of the resources, user can have opportunistic usage of unused resources. So user can either own their resources and use our services to federate them and have easy access to them, or use the resources already in the available in the infrastructure to in an opportunistic way. So that means that they are not dedicated to your organization, but since you are enabled in these resources as part of the EGI infrastructure, you can access when let's say the resource centers have some spare resources, you can access them. And in this way also the resource provider are more happy, let's say, because their resources are used in a more efficient way. Now I would like to spend a few minutes describing how authorization and authentication are handled in the EGI infrastructure. So EGI is a multidisciplinary infrastructure. That means that the same resources are shared among different research communities. Research communities access the infrastructure by grouping their users in virtual organizations. Let's say usually there is a one-to-one mapping between virtual research community, let's say a research community and a virtual organization. This is not mandatory though, so there are big communities who are, let's say, enabling different virtual organizations for the different disciplines they include, for example. And these these virtual organizations are basically groups of users, and they are enabled on the resources. So users are not individually enabled in the resources, but resources enable virtual organization. Of course, there are finer grained authorization mechanisms beside the virtual organization. This is basically how users can enable resources. They can ask to have their virtual organization enabled in a site. How users are authenticated? Well, authentication in EGI is based on X509 certificate. The certificates are issued by certification authorities, part of the EUGRID PMA Federation, which is also part of the IGTF Federation, that is International Grid Trust Federation. What users should do is to request their credentials, so to request a certificate to a registration authority. What is important is to get a certificate for an EUGRID PMA certification authority. If you need more information, I put a link here. And all the EGI sites contain accept certificates, part of the EUGRID PMA distribution. That means that if your VO is enabled on that site, also your certificate will be accepted because all the certificates are recognized at site level. Usually these are used in let's say by command line tools, but they can be used also, well, you know that a certificate can be stored in a web browser and used to access the services that we are providing through websites. The user authorization is not handled at user level, but usually site authorize access to their resources to virtual organization. So they enable their, they use virtual organization for their access policies, for resource allocation. So how many resources is a virtual organization allowed to use? As I was saying, there are finer authorization policies. There are groups, there are roles within a virtual organization. So the users can be structured within the virtual organization, and is not a 0-1 authorization policy. All these details within the virtual organization are managed directly by the virtual organization, the VO managers, using the virtual organization membership service. It is called VOMS, and they can do it independently, so they can manage their users and their authorization policies. What users do usually to submit any task to the infrastructure is they attach to the task their credential, and their credential attached with a proxy certificate is a short-term credential signed with the user certificate, and it is extended by with the virtual organization attribute. So let's say the user certificates are generic; they are just ID. The proxies contains also the virtual organization details. So a site receiving this proxy recognize that a user is part of a virtual organization with such role from such group. And of course, users part of multiple virtual organizations can generate multiple proxies. In summary, the pros and cons of X509. The pros are that transparent authentication throughout all the services in the distributed infrastructure, and this is a big pro. So you are recognized as you in all the services you are accessing using your certificate. And also the authorization, the access control can be handled, let's say, in a uniform way using virtual organization. The cons of the certificate are that, of course, if you already have your credential, you need an additional credential, so you cannot use your institutional one. There is need for a face-to-face ID confirmation with the registration authorities who are distributed, let's say, in all the countries part of EGI, but this may be tricky if you are not, let's say, you have not a registration authority in your institution. And well, yeah, it was thought to be used with a command line tools, but this is not mandatory, as we will see. So now I have a set of slides about the storage and data management services that we are providing in EGI. So how data management works in the grid. So data can be stored on different storage systems. There are distributed services, but there are also a lot of different implementation of storage services that we are actually providing in EGI, but they are accessible, let's say, with common interfaces. So different technologies access through common interfaces. This is how the grid works. There are different distributed storage services, so data can be distributed and replicated among different locations. To handle this distributed environment, there is need for file replica catalog, metadata catalogs, and file transfer services to replicate and move data between sites. The SRM is the most common interface, the most common protocol that users use to access data. We have three big implementation of storage services. It's DPM, Dcache, and Storm. They are providing similar features from a user point of view. So they expose an SRM interface that can be used both by users and applications. That means that what happens very often is that computing tasks access data, input and output data through SRM. SRM allows quite fine-grained file management, Also, there are some space allocation, pre-allocation tools if needed, and the file transfers are then handled. Well, they go through or the grid FTP protocol or HTTP. So SRM is a data management, let's say, interface, but the actual transfer are executed through grid FTP. As I was saying, there is need in a distributed environment, particularly there is need for a file catalog. So, which is the more common implementation is LFC, so logical file name catalog, and what it does, it stores logical file names that are user created alias to refer to a data item they uploaded to the grid. It keeps track of the data location and the data replicas. So the physical, let's say, location of the data, it maps between logical ID and physical ID of the data, and it gives additional access control features based on the virtual organization, for example. So what a user does is to query the LFC server, getting using a logical file name, and he gets back the physical location of a file. If there are multiple replicas, of course, it will choose one of these replicas and download the file. So here I have let's say an example of how data management can work in the grid environment. Storage services are publishing their information, so what their resources they are providing, how space is available, which virtual organizations are allowed to store data in the services in the information system. So user usually query the information system to find services they can use with their virtual organization. They get, of course, the credential from the VOMs, as I was describing before, and then basically they upload with the same command, with the same tools. They upload the file in the storage service and register a new entry in the file catalog in the LFC. So they have their data stored in the grid, and they have associated a logical file name, which is a mnemonic file name that can be created, well, which is created by the user, so can also contain some logic typical of the user workflow. So metadata are in the file catalog, and the actual data are stored in distributed services across the infrastructure. I have a couple of slides about the file transfer services. The first one is FTS. File transfer service, basically they work, all of them, in a similar way. They allow to schedule data transfer between storage services deployed in a distributed geographical infrastructure, that means in different sites. Users can submit and monitor the status of multiple data transfers, so there is no need for the user to execute physically the data transfers. The user can submit these data transfer to the FTS and wait until they are executed, because FTS also tries to optimize these data transfer between sites. It's a command line tool and is fully integrated with the virtual organization authorization that I described before. It is intensively used by the LHC VOs, by the high energy physics VO. That means that it is widely deployed and widely used, accessible in the infrastructure. The other one is Global. It is a very similar service, so allows users to manage data with a user-friendly web interface. The difference is that Globus Online is, I would say, more user-friendly and is still a powerful tool. It is basically handle the user authentication on the grid services. All the transfers are performed using grid FTP, which is supported by all the storage services deployed in the infrastructure. And there are there is also a client tool that allows easy access to the files from the laptop. So basically, Globus Online can be used to upload from the local computer to storage service in the infrastructure and move data among storage services, because of users may want to replicate data, may want to move the data in order to have data available in a site they know they will be using in the future. And this is accessible in this through this website. globusonline.eu is the European version of it. It is this website, let's say this is operated by the European Globus Community Forum, which also produces distribute Globus middleware for EGI. Beside the data service that we discussed now, data usually data needs to be processed, and so together with data we provide also computing services. Computing resources are usually accessible through grid interface, and this interface we call it computing element. We have several implementations of this computing element. Let's say they are CREAM, ArcC, Globus, or Unicore services. And basically the purpose of these interfaces, these grid interfaces, is to allow users to submit computing tasks to the clusters that are installed in the different resource centers in the EGI infrastructure. So they are common. They provide common interfaces to access physical resources, computing resources in the EGI site. The computing elements are published in the information system I briefly described before. The available resources they are offering, and the virtual organization supported by the site. So users know if these resources can be accessed by their group of researchers. Users can directly submit to the computing element, so they can choose a site from the information system that they like it because they know that they already have the data there, for example, or they have been happy with the services provided by that site. They can submit their jobs, their computing tasks, and monitor their status and get the output while they are done. Usually data input and output are staged in and staged out to grid storage services. So the storage services that I described before, and let's say and download them afterwards. Of course, small outputs can be like log files or something like that, can be directly downloaded from the computing elements. The users usually what users do is to provide an execution environment answering to the in question to their jobs. So usually virtual organization can set up a software area in the nodes where jobs are executed, and this is part of the, let's say, of the negotiation, let's say, not a real negotiation, but let's call it like this, between users and sites. So virtual organization publish their requirement, and then site, if they want to enable a virtual organization, they will go through the requirement and see if their site can support a virtual organization, and if needed, they will also set up software environment for the virtual organization. Most users, most sites, what they do is to enable write access to the software area of the virtual organization for specific roles within the organization. That means that there are expert users within the VO that can upload their software in the software area for their VO and set up the execution environment for their tasks. Other virtual organization, they just bring all the libraries with the job execution. So it depends. There are different ways to prepare the customize, let's say, these computing elements. And we are, for example, starting a pilot with a central automated way to distribute software, which is called CERN Virtual Machine File System, but it's not about virtual machine. In this case, it's about really distributing software in a uniform way, easy way to all the sites. So there are different ways user can customize the execution environment. Another, well, as I said, the user can go directly to a computing elements, but since there are usually multiple resources supporting the users, and there may be a site with a lot of more resources than other sites where users can submit and run their job immediately. Usually a good practice is to assess computing resources through a workload management service that is basically a broker for the computing resources. The EMI WMS is the most common workload management system in EGI, and users submit directly to the WMS their jobs, specifying the requirements for their jobs. The WMS retrieves for the information system the list of computing elements compatible with the job requirements, and the jobs are submitted to the computing elements that fit the requirement and with a lower workload. So where the user have the higher probability to run in the smaller time their jobs. Jobs can be monitored and the output retrieved directly to the WMS once they are completed. So this is a similar slide for the computing workflow. Batch processing, and a user gets his credential as usual, contact the broker service, so the WMS that I was describing in the previous slide. WMS gets from the information system the list of CEs of computing elements where the job can be submitted, logs, keep the logs and the status of the job, where the job have been submitted, and submit the list of jobs in the computing services in one site or in different sites. And once the job is executed, the job status is reported to the broker, let's say to the login and bookkeeping service of the broker, and the user can monitor the status of the job and retrieve the outputs of the job if they are small output like log file or just the status of the job at the end of the execution from the broker. So I have a few slides about the science gateways. All the services that I described before, they have pretty much all, they have command line client or APIs to be used to access these services. But of course, what many communities do is to build on top of the services that I described before. There are community-specific tools that are usually users have a set of tools, a set of applications they run, and this can be integrated in a single web portal or a desktop application, for example, so users can interact with the EGI resources in an easy way. Let's say also, since the use case may be similar between different users within the same virtual organization, a set of predefined tools of action can be implemented in this web portal to make it easier and quick to submit, for example, a big number of jobs with one click. This is of course to make simpler the access of users to these resources, and of course these are all, let's say, user specific, but the components building these gateways, these portals, are pretty much common, because you need to have, for example, to handle the authentication, the proxies, to create a proxy if needed for the user. So there are a set of common tools that can be shared between among the virtual organizations of EGIs, and for this there is the application database of EGIs that can provide information about the already existing solutions. Of course, one of the point of using this web access tool is to continue to use the institutional username and password if the portal logic does let's say, handle the user certificate. This slide basically shows a very simple schema of how the EGI infrastructure tools work. There are the set of data and compute services I described in the first part of this presentation that usually handle the access to the physical resources. So what users do is to directly go and use this workload management system, these file transfer services, to access, let's say, to use the physical resources through the data and compute services, the orange box, or as described in, let's say, in the last slide, use community-specific services or workflows, their own tools or tools built by other user communities that then interface, let's say, they lay on top of the data and compute services, they interface with the common interfaces provided by the tools that let's say, expose the physical resources. And these, let's say, data and compute services are then interfaced also with the core services, which are the tools, the services that enable the federation, because federation is not only about accessing services, but also providing other, let's say, accessing resources, sorry, but also about accessing other services, other tools that are needed in a distributed collaboration environment. So what are the core services provided by EGI? There are a set of core services that EGI is providing centrally or that are distributed, provided by the NGIs, but they are basically these. So for the resource discovery, service discovery, we have a central service registry called GogDB. It's a semi-static list of production services. Semi-static means that they can be updated, but they are not automatically updated by services. So it's site managers, resource centers manager, or NGI managers. They log in and change by hand these information. And this is useful because we need to know if a service is in downtime. We need to know that there should be a service supposed to be in production. This service GogDB also contains the service downtime registry. So if there is any maintenance scheduled for services, you will find in this tool which are the services affected. The information system that was described before, it's let's say a more dynamic information service. So services are automatically registering there. So once a service is on, it appears in the information system. There are some semi-static information like the VO supported by the services, but also other dynamic information such as the amount of resources currently available, so currently free for usage. And these has also a cache system, so information are cached for a few hours, and after the so if a service disappears for any glitch, it will stay in the information system with a note that the information were cached. So user can always distinguish between fresh information and cached informations. These information are published by a set of services called BDII. All the BDII include the same set of information. They are usually provided roughly 1 or 2 by every NGI. So there are several of them, many of them in Europe to be used. There is no authentication authorization to access them, so users can use the BDIs they want. And they are high available services, so NGIs are assuring 99% of that of availability. To monitor the infrastructure, there is a distributed service availability monitoring called SAM. Basically what it does, it monitors the availability of the services, emulating the user behavior, testing the interfaces exposed by the services. So they're trying to submit a job, to upload a file to a services, etc. There are other support tools like the operation dashboard used by the NGIs to check the errors, the alarms generated by the services. So it's more an operational tool used by NGI's teams. And of course, EGI provides a central help desk service, so where user can file incident report. The help desk is used by users to submit incident report, like I have trouble accessing these resources, or my file has disappeared because the storage element is in downtime. What can I do to recover it? And EGI provides a first or second level support. That means that there is a ticket triage service, so tickets are redirected to the correct support tuning, to the correct site or NGIs. For technological support, there is also a support unit that helps with the middleware services, so the usage of the middleware services, if there is any problem with them. And also technology providers, so the many developers who are providing software to us are also providing support through GIGAS. Sorry, we didn't write it here, but it's the name of the service, GIGAS. As I said, NGIs and site are accessible to the help desk. If users have problem with the NGI or site, they can submit a ticket. And why it's better to submit a GIGAS ticket rather than sending an email to a site? Well, first of all, sites have an OLA for to provide a service level for the help desk. They don't have it for emails. And also in case of let's say problems that affect multiple services, multiple sites, with a GIGAS ticket, it's easy to reassign, to redirect the ticket to another site. So I always suggest users to use our help desk. And also, I didn't write it here, but EGI provides a accounting system. So the resource usage is accounted at VO level, sometimes a user level, but of course confidential information such as the individual users usage data is not accessible to everyone, is accessible only within the virtual organization and only by authorized users within the virtual organization. So apologies for missing this on this slide, but this is basically the other core service that is very interesting for user communities. Currently, we are accounting for compute because it's, let's say, easier. But we have the technical tools to account also for storage, and we are trying to deploy it in our infrastructure. So we are we are working with our technology providers who provided the technical tools to do storage accounting, and with the let's say the accounting team to deploy a storage accounting system, so we can account for both compute and storage. So just concluding the presentation, and then I will leave room for other questions. What are the EGI services? So high-throughput services for data and compute tasks, and I described them. During this presentation. They provide uniform access to distributed heterogeneous resources. That means that you can use distributed resources in different size, managed by different administrators, and you can use them in the same way. That means using the same tools to access them, the same interfaces, same protocols, and also being authenticated and authorized on these resources, which is not trivial. So you will have your user authenticated in different in all the sites in the same way. You will have your virtual organization, your user group able to manage data based on the access policies that you have set up by all the resource centers in EGI. On top of that, of course, we provide a set of other services like this user support, like the other core services that I described in the last slide. Okay, so I see a question. What are the biggest data currently managed? This is a good question. There are virtual organizations storing around a petabyte of data. In the biggest one, of course, the high energy physics is the biggest community we have, and basically they are handling this amount of data. Of course, if you're referring to a single data set, I'm not sure about the size of a single data set that is usually handled by a virtual organization. So, well, by a users or a group of users within a virtual organization, because this is mainly handled by the virtual organization itself. But as amount of data, yes, we have virtual organization using several petabytes of data storage, considering also the fact that data is often replicated to be easily accessed. Yes, question, Leonardo?
So the question is, how do you reconcile WebDAV with the certificate stubs?
This is, of course, the full authorization using VO is currently accessible through to the SRM protocol, which is the grid most common protocol to access and manage data. But WebDAV can through, let's say, WebDAV being HTTP based, can be HTTPS based, so you can use WebDAV with your grid certificate. Most of the other grid services are web services. Not all of them are the HTTP based, but for this specific WebDAV and HTTP data transfers, what is the plan is to use the certificate over a HTTPS connection. And this is something that is getting more common. So it's not, WebDAV is not the most common currently access protocol, but this is something that the biggest virtual organization in EGI are pushing, and so sites and technology providers are enabling WebDAV access to the storage services. There was a question from Leonardo.
So my question is, what are the, let's say, the approach that a community or someone should put in place in order to build its own gateway? And the second is, I assume that the gateway constituent are portlets. If this is not correct, please, could you tell us what kind of component do you integrate in building a gateway. And the third is more than a question, is actually a comment. So I don't know if you are familiar with the notion of virtual research environment and with the approach that has been put in place in the context of the G-Cube technology for building what we call it in that context virtual research environment that to some extent are a kind of gateway that are dynamically built and they are built in a very simple way. So the user that is defining a gateway should not bother with acquiring application from one place and deploying it manually.
I would ask if Gregory has some comments about that, because his team is following more closely all these activities around Liferay and Science Gateways.
So I'm Gergely, working in the user community support team in EGI.eu, and the answer to your question is, for the first question, how to build a gateway. The screenshot is not up to date that Peter used. If you go to the applications database today, you will see two types of Science Gateway categories on the left side. You can see Science Gateway instances, those that are shown on Peter's slide, and you can see Science Gateway frameworks, those that enable anyone to build a Science Gateway instance for themselves. Many of these Science Gateways use portlets as building blocks. So building a Science Gateway means that you define a portlet on top of some scientific application or scientific workflow or scientific database that you want to orchestrate through the web interface. So there are several projects, there are several technologies out there that helps communities to build Science Gateways for themselves. And we know about G-Cube. G-Cube, I'm sure, is on that list as well. I need to check, I don't know from the top of my head, but we are promoting that as well alongside with other technologies. And yes, the terminology is fuzzy. Some communities call it Science Gateway, other communities use it as virtual research environment, yet another communities call it e-laboratories, and so on and so forth. So these roughly mean the same thing, very strongly web-based, and bringing together different kind of data sources, data technologies, workload management systems, and underlying cloud or grid-based resources.
Thank you for Gregory for providing more details about that. And this is pretty much it for this presentation.